P.1 real numbers and their properties. So the first thing we want to talk about are the types of real numbers. And we want to note that every real number can be written as a decimal. So natural numbers, aka counting numbers, are those ones you learn as a child on your fingers. They're the ones you would count naturally. 1, 2, 3, 4. Our whole numbers are 0, 1, 2, 3, 4. So all the counting also 0. Our integers are whole numbers and their opposites, so we also go in the negative direction. Rational numbers are numbers that can be written in the form of a over b, so as a fraction, where a and b are both integers and b cannot be 0, because if it is, then it's undefined. So basically is a ratio of integers. And then lastly, we have our irrational numbers, and those are numbers that cannot be written as a ratio of integers. Whoops, missed a couple pages. Okay, so for the real number system, some examples we might see of, say, rational numbers could be like negative 6 over 5 or 3.4 repeating, right? Or a third, right? A third would be 0.3 repeating. A type of rational could be an integer, and that could be, say, negative 6 over 3. That would be negative 2, really, or negative 4. Whole numbers could be something like 0, right? And our natural numbers are numbers like 1, 2, 3. So we might have like 3, we might have 7, 999 would be natural. Even the square root of 25, because really that's just the number 5. However, on the irrational side, those would be numbers we cannot write as a fraction. There's some sort of decimal that goes on and on with no pattern. So that could be like pi. That could be the square root of 2, the square root of 3, the square root of 5, and eventually we'll talk about this year. There's a number called e, and that is also an irrational number. All right, so in our first example, we're going to evaluate an arithmetic expression. So we have to find the value, basically without a calculator. We're doing the order of operations. So you probably learned PEMDAS in middle school. We're going to do our grouping symbols first, our parentheses, our brackets, our braces, then exponents, multiply and divide left to right, and then add and subtract. So if we take a look here, we see our parentheses. We definitely want to work inside out. So we've got the 3 on the outside. That's not going to change. And then we see this fraction bar. So we want to make sure we do the things above it and the things below it separately before we do that division. So that's 18, 8 plus 10. 2 times 3 is 6, plus 4. And then we have the minus 2, and we might as well do these parentheses now. So 5 and 9 makes 14. All right, so 3 times 18 divided by 6 is 3, plus 4, minus 2 times 14. And then 3 plus 4 is 7. And then we'll multiply and get 21 minus 28, and that subtracts to negative 7. Some properties of real numbers. I'm sure these look familiar to you. We have commutative properties, which means we can add or multiply in any order. Associative properties, which means basically something similar, but we can group them and it does not matter. So I can add A and B first and then add C, or I can add B and C first and then add A. Same concept with multiplication. The distributive property, as you know from, when you learned it in Algebra 1, is just multiplying to everything inside those parentheses. And then for addition and subtraction, we know that the number 0 is called the additive identity because when we add 0, it doesn't change anything. So a plus 0 is still a. And then every real number also has a negative version or an opposite. So if we have the number a, negative a would be our opposite. And when we add those two together, a plus negative a, they should cancel each other out and give us 0. And we know that subtraction is the operation that undoes addition. We also have some properties for negatives. So when I multiply by negative 1, it's like just tacking on a negative sign, or really changing the sign of the number. The double negative in the second one makes it positive. And then when I multiply a negative times a positive, my product will be negative. When I multiply two negatives, I get a positive. When I distribute a negative, that's going to change all the signs on the inside. All right, so multiplication and division, we know that the number 1 is called the multiplicative identity. Much like the additive identity, it does not change the original value. So when I multiply by 1, nothing happens. Every non-zero real number also has an inverse. So an inverse is basically taking whatever the value is and putting it underneath 1. So if I have the number 7, 1 over 7. If I have the number 1/3, it would be 3. So basically we're flipping our fraction over. Division is the operation that undoes multiplication, and to divide by a number, we multiply by the inverse of that number. So really when we say that we are dividing by 7, it's like multiplying by 1 over 7. A over B is the quotient of A and B. Quotient's the answer to a division problem. And A is the numerator, B is the denominator or the divisor in this case. We also have some properties of fractions. If you remember, for multiplication, we just multiply the numerators and multiply the denominators straight across. In division, very similarly, we're going to do something like this, but instead what we need to do is multiply by the reciprocal. You may have learned a little trick called keep, change, flip, or something along those lines. For addition, we need a common denominator. It does not have to be the least common, but it certainly makes life easier if it is the smallest common denominator. And same for subtraction. That's also a requirement. And then we know that if we have common factors in the numerator and denominator, we can divide those out or cancel them out. And if we know that we have two fractions that are equal to each other, we can use cross multiplication to basically eliminate the fractions and just make one line of an equation. All right, so in this example, we are going to evaluate. So we need a common denominator here. So I see 36 and 120, and those numbers, let's see, 360, I believe, is going to cut it. So if we multiply the first fraction by 10 over 10, really that's like multiplying by 1, right? If we multiply the second fraction by 3 over 3, that'll make both of our denominators 360. So that makes us 50 over 360 plus 21 over 360, and then I add them together. So the numerators make 71 and the 360 stays the same. Repeating decimals. So we can express any repeating decimal as a fraction, and this is kind of a neat trick. I know you probably have some memorized, for example, that a third is 0.3 repeating. But for the most part, these are not ones you just know off the top of your head. So here's kind of the trick, okay? We're going to say that x is equal to this decimal, and we're going to write it out just a little bit. So we'll say that x is equal to 0.777, and we would keep going. Well, I can multiply both sides of this equation by any number I want, and it would still be equal. So I'm going to multiply both sides of this equation by 10, but I'm going to just write it as a separate equation. So if I multiply x by 10, that's 10x. If I multiply 0.7 repeating by 10, that gives me 7.777, and it continues on, okay? So far, all I did was just write an equivalent equation, and the purpose of multiplying by 10 was really to force the decimal place to move over 1. Now what I can do is subtract the equations from each other. If I subtract 10 minus 1x is 9x, and over here, the repeated portion will cancel out, and I'm just left with 7. Now I can solve for x, and I get that x is equal to 7 divided by 9, which is kind of a neat trick. Let's try another one. So we have that x is equal to 0.2888 and so on. And really, if I think about it, what I want to have cancel out is the 0.8, right? Before I needed the 0.7 to disappear, now I need the 0.8 to disappear. So if I were to move the decimal over one space to the right, that would leave me with 0.8s, and I could start to get rid of some information here. However, that's not really going to fix the problem because I still have to deal with that too. So here's what I can do. First, let's make it so that the only thing to the right of the decimal point is the repeated part. So let's get rid of that too entirely. We can do that by multiplying by 10. So I have 10x is equal to 2.888 and so on, okay? I can't do what I did before, because if I were just to combine these, I would be left with, on the right-hand side, if I subtracted, I'd be left with 2.6, and that's not quite what we're going for here. But what I could do is to then create another equivalent equation from this. So just like I did before, if I think of this as the original equation, I could multiply again by 10, so that would give me 100x. If I multiply the right by 10, that gives me 28.8 repeating. And then I can subtract, and the 0.8s are going to cancel out. So that's, let's see, 90x is equal to 26. Okay. And then I could divide by 90 on both sides, and I get x is equal to 26 over 90. Okay. And one last one. This is a little bit trickier, but it's actually not too terrible because this is two numbers that are repeating. Last time it was only one number that was repeating. So we have that x is equal to 0.575757 and so on. So what I want, remember, is only the repeated part to the right of the decimal, which is currently the case, right? Just like in the first problem. But if I were to move this decimal place over to the right twice, that would still leave me with 575757 at the end that could cancel out. So to move the decimal twice, we're going to multiply by 100. In the first one, we only wanted to move the decimal once, so we multiplied by 10. Right, so if we multiply by 100, that makes 57 point, and there's my 575757. Again, I'm going to subtract. So that's 99x is equal to 57. Divide, so x will be 57 over 99. In example 4, we have the area of a garden. So Mary's backyard vegetable garden measures 20 feet by 30 feet. So its area would then be 600 feet squared or square feet. She decides to make it longer as shown in the figure. So we see this dotted area that's being added on. And we want to find the area of Mary's new garden. So obviously it's going to have an X in it, but we do want to write this out. So the 20 foot is staying the same, but she's making it longer. So what that is doing is changing the length to 30 plus X. So now when I find the area, I'm multiplying the length and width together. So the new area is going to be 20 times 30 plus X, which is going to give us 600 plus 20X square feet or feet squared. So this is our new area. All right, and lastly, we know that addition and multiplication are both commutative operations. So we want to know a few things. Is subtraction then commutative? Can I subtract in any order? The answer to that, of course, is no. If I were to test that, I could do 2 minus 3, and that is not going to be the same as 3 minus 2. It'll be similar, but it'll be opposite answers. Is division of non-zero real numbers commutative? Can I divide in any order? Again, the answer is no. 1 divided by 2 is 0.5. 2 divided by 1 is 2. Are the actions of putting on your socks and putting on your shoes commutative? Does it matter if I put on my socks first or my shoes first? Of course it matters. So the answer is no. It does matter what order we put our shoes or socks on first. It'd look a little silly, shoes first, don't you think? Are the actions of putting your hat on and putting your coat on commutative? The answer there is yes. It does not matter which one goes on first. And are the actions of washing laundry and drying it commutative? I would hope not. It does matter whether you wash your clothes first or you dry them first.